Hello everyone, my name is Sahil, and today I'll be speaking about adversarial online classification with a sample preview. This is joint work with Livni from Tel Aviv. So let's start with what's a classification problem. The historical examples are, let's say, you've given images, you want to identify whether it's a cat or a dog, you're getting emails, you want to identify whether it's a spam or not a spam, in general, like, or you're getting some loan applications and you need to decide whether to approve or not. So classification is basically like you need to somehow come up with a decision, like usually like a yes/no decision, uh, and given some features about the space, so about the problem. So more formally, the classic formal model is the following. You have an instance space X. So this is often infinite, like this is basically some features like the pixels of your image. So this is the instance space. There's the label space, which usually like the yes/no kind of a case. It's often binary, like 0, 1. So whether you pass the loan or not, cat or a dog. And you have some hypothesis class. So this is whatever like machine learning application you're learning. You might be doing a hypothesis such as like half spaces and so on. And the goal is that, okay, you're going to get some instance. You have to play a hypothesis. And then hypothesis is basically a function which, when applied on X, will give you some label, like some usually like a 0, 1 label. And then the real label will be revealed, like your email got received, you labeled it spam, but then you'll get some feedback that, okay, whether the data was actually, the email was actual spam or not. So a mistake is basically if h of x is like your prediction is not the same as the true label. And at a high level, the objective is to find the H, the hypothesis, that minimizes the number of mistakes. So we'll formalize this even further on the next slide. But that's the classic classification problem. So one thing to note, like it's called classification because whenever I make a prediction, either I'll be correct or wrong. So like my reward in some sense is 0 or 1, reward or loss. Unlike regression, where let's say if you make a prediction, I might also have some notion of distance. How far am I from the real answer? Here, the distance is basically just literally 0, 1, like either you're correct or not. Good. And people study this problem, like, yeah, very general label spaces, very general instances, and very general hypothesis classes. So let's look at what is known about learning. So firstly, the classical statistical learning or offline learning is the following, like which goes back to at least the model of 9, like Leslie variant from the 80s. Here the setup is that, okay, there is some underlying unknown distribution. Good. So unknown distribution D, and you're given a bunch of labeled samples, xi, yi, from this distribution. Usually, let's say I'm giving you some n labels. And the goal is to find a hypothesis h hat such that the probability, you want to minimize the error probability, which is probability of h hat x being not equal to y. So this is the probability that you make an error if I draw a fresh sample xy from the underlying distribution. And what you're usually comparing, this is kind of the hindsight out, which is that if you whatever is the best possible hypothesis, how well do I perform compared to it? So this is the question we're trying to interest in. Notice like the second term is kind of a constant. But like I usually want to think of the gap between the two. Good. So this is the offline learning. People have also studied this problem a lot, even in the online context where the entire data is not known upfront. So this again goes back to the work like back in the 80s, like already studied by Littlestone and all, and generalized and extended by the work of Bendermid, and Schwartz in 2009. Here the setup is basically like rather than giving you all the data upfront, you receive some like instance xt, you have to make a prediction. Then you're going to observe the true label white, and then you'll get like some loss, which is whether you're correct or not. And then you repeat. So I'm going to give you the xt plus 1, you have to make another prediction, and so on. So the catch here is it's an adversarial sequence of arrivals, unlike like the IID arrivals above there. And the goal usually here is to minimize regret, which is the number of mistakes that the algorithm makes, versus like the minus the number of mistakes by the best fixed hypothesis in hindsight. Right? So this is again both classical like online learning. And we want to study these classification problems. So what's at a high level known about this problem? So at a high level, like these are again classical results, are that statistical learning or the offline learning was basically governed by something called as the VC dimension. So if your problem, like your hypothesis class, has a small VC dimension, then you can learn it fast. You can find the optimal hypothesis. On the other hand, when it's online learning, there's something called as the Littlestone dimension, which is usually much larger. So, but if the Littlestone dimension is small, then you can learn, but otherwise you cannot learn. So the precise definitions of these VC dimension and Littlestone dimension will not be important for this talk. In fact, like I'm going to talk about a very simple example, and this the example is the main to keep in mind. So the example is this called as the threshold example. So what do I mean by this? Imagine there's like a unit interval 0 to 1, and every possible threshold, like a scalar in the 0 to 1, is a potential hypothesis. So what is the prediction of that hypothesis going to be? Like anything to the left of it is going to be 0, anything to the right is going to be 1. Good. So that's the hypothesis. And so the goal is basically to figure out what's the best hypothesis. In some sense, you want to figure out what's the best threshold theta, such that like that label on one side is this thing, and the data underlying the distribution is coming from this side, such that the prediction on one side is 0 and the other side is 1. Good. And if the underlying distribution, like whatever is the unknown distribution, it's basically IID arrivals, it's easy to show that you can actually learn this threshold pretty well. So morally, you can say like, okay, after like roughly 1 over epsilon squared samples, I can identify the exact threshold up to plus minus epsilon. So the kind of regret or the thing we'll get is something like going to be square root t. So after t arrivals, there's going to be like, we have to pay some kind of a standard deviation. So square root t you have to pay, but not more. And this threshold example that I've told you is the classic one-dimensional version. It has VC dimension 1. But yeah, I mean, like you can generalize this, and like there are many interesting examples with small VC dimension. But for this talk, it's not important to know what is even the formal definition of VC dimension. The goal is precisely that, okay, how do like this threshold example is very easy to learn offline. In contrast, when we go to the online learning world, this turns out to be the threshold is already very bad. So what's the setup? Like it's basically I claim that basically the regret or any algorithm in this online learning model, even for thresholds, has to pay omega t. So linear in t. T is the number of rounds. Regret. So, and what's the counter example? Like what's the bad example? It's basically some kind of a binary search. So the setup will be something like the following, like the adversary in the beginning gives you the middle point. Of this unit interval, you have to predict 0 or 1. Okay, you maybe predict 0 or 1, whichever way. The adversary is going to now toss a point. With 50% chance it's going to the left, with 50% chance it's going to be going to the right. So there's only a 50% chance that you'll be correct, otherwise 50% chance you'll be correct. Let's say the adversary goes left. Again, you make some prediction, yes or no, like 0 or 1. Again, the adversary will go like with 50% chance left and right. So basically, you can do some kind of a binary search. Then you have this tree of height capital T. And every time step, your algorithm is basically being incorrect with half a chance. So every online algorithm has to pay at least t over 2 regret. Because in hindsight, there will be like this particular threshold, which is given by the leaf of this binary search tree, says that everything to the left was one label, everything to the right was the other label. And there's no way your algorithm could have guessed it because, it was generated through this online process, stochastic random process. And this exactly is the reason why the Littlestone dimension for this instance turns out to be large, and basically the regret is omega t. So the precise question we are interested in is, okay, how can we get like regret roughly square root t? Square root t kind of you have to pay anyways in the online setup because of even standard deviation like variance. So the precise question, that's why we are asking is, how can we go beyond this worst case for online arrivals? So we want to understand this online problem of online learning problem, online classification. But now we don't want to consider the fully worst case where you have no idea about this arrival sequence, because if it's fully adversarial, then somehow you cannot go past this omega t barrier. You have to pay omega t regret. And you want to get square root t-ish. Right? So one way of doing this beyond worst case is to assume some kind of IID or stochastic arrivals, like in random order arrivals. So IID arrival will basically mean that, okay, there's some underlying distribution, unknown distribution, from which you're getting these points xy. And or like random order will be like a close analog is like, okay, there's some xy labels and then the adversary like just randomly permutes them. And then you're getting these one at a time. And you have to make these predictions. Turns out this IID model, like although the process makes sense, for this online classification problem, it's like not so interesting. Basically, what you can do is the claim is that it's pretty much basically like the offline learning or the statistical learning problem. What you can do is like, because every prefix is kind of like a representative of the entire distribution, you can more or less run the offline algorithm. So on this entire data. Or alternatively, you can do some kind of a doubling trick, like use the first k samples offline, come up with a hypothesis at 2k samples, update the hypothesis, and so on. So in short, this crucially uses the fact that, okay, your adversarial arrival process has kind of very much changed. It's no longer adversarial, everything is kind of jumbled up. Hence, in some sense, like the past represents basically the entire future. And some VC-based methods, again, will basically work and you'll get the same kind of bounds. The catch is that, okay, we've made some kind of very strong assumption that the arrival process is fully IID or fully random, like past represents the future. So the question basically is that, okay, can I get something much better? Like for like something like, let's say like a square root T regret for this threshold example, without making this full IID random order assumption. And like there is like very interesting work in this IID and random order model. For instance, like Stefano Leonardi's group had a result on this, but like, yeah, we want to get like more interesting, like rather than the simple black box reductions to statistical learning. And this brings us to the model that we'll be studying in this work, which is called as the sample preview model. And this is very closely related to like similar models that have been studied in online algorithms, like online algorithms with sample model or the p-sample model and so on. The setup is the following, that the adversary fixes a full sequence. So it's a fully adversarial sequence of capital T arrivals. Good. So each point here is basically a xt comma yt label. The adversary chooses both the instance as well as the label, like a 0, 1 cat dog kind of a label. But then once the adversary fixes this entire sequence, a random p fraction of this, think of p like this is the rate of the preview. Think of p as like, let's say 1%. So a random 1% of this online sequence is going to be revealed to you upfront at time 0. Okay, so each input, let's say, gets revealed with probability 1%. Okay, so and the question basically, I'll make this formula a little bit. But the question then becomes like, how would I design a good online algorithm for the remaining 99% of the input? Okay, so these red points in this image are the ones which are kind of revealed, and the others you still have to. So more formally, before the prediction begins, you are revealed a sample which is of size exactly pt uniformly at random. Okay, so you basically on average, like each point is getting revealed with probability p. When you're revealed both like its position, its instance, as well as its label. And then the online phase begins, where all the remaining, these are I'm calling the real requests, which is all the T requests minus the sample, they're going to be arriving exactly in the original adversarial order. So there's no like stochasticity on that. It's arriving in the same order, and then you play the same online prediction game. XT is revealed, you predict some YT hat, and then you reveal YT. The question is again, okay, how can I now use this small preview? Like, so this is what we're calling preview, like so the 1% sample that's revealed to you upfront. And the goal is to minimize my regret. And I'm going to compare again myself to like some kind of the hindsight optimum. What's the hindsight optimum is like, let's look at the hindsight optimum of the entire sequence, look at its performance on the remaining 99%. So the question is now, because like you're still getting pretty much like T arrivals or like 99.99 times T, can I get my regret much smaller, like then omega T, can I get it like something up to square root T? That's the high level question. So this is what we're calling adversarial online classification with preview. Okay. So again, like to get a little bit intuition, let's say when p is extremely small, when pt is less than 1, let's say, then basically you're not getting any sample. Okay, so if p is so small, p is like less than 1 over t, and you're not getting any sample, so you're back to basically this adversarial setting. And so the binary search example that we saw, you can still applies, you'll have omega t regret. On the other hand, when p becomes like a constant, actually like when p is like 1% or any constant, then you're kind of getting revealed like omega t fraction, constant fraction of the samples. Then what you can do is like argue is that basically it's as if you're back to the offline problem. Because you can imagine there's like a distribution, which is uniform arrival over these t sac arrivals. And if you reveal me like a very significant portion of this distribution, then of course you want to learn everything about the distribution and you can get back to low root t regret. And let's like for simplicity again, like, keep the threshold example in mind, which has VC dimension 1. So the real question is what happens if P is somewhere in between? Good. So if P is extremely small, nothing can be done. If P is significantly large, then okay, you're back to square root T. The problem is trivial. And the question is really, okay, how large the P or P times T needs to be. So let's say there's a precise question like which I would encourage you to try to answer. So the question is, what's the smallest PT? Like recall PT is the size of the preview that you're given that admits square root T for the threshold example. So A option, we know like theta T definitely works. So if I reveal you like a constant fraction, then you'll be done. But what if I reveal you like T to the 3/4? Okay, will that work? What if I reveal you square root T fraction? So remember, overall you have T arrivals. Which of the three is the smallest answer? Okay, and more generally, we want to understand, like not just the smallest PT which admits square root T regret, we want to understand what the real trade-off between what the regret we are getting and what is the size of the preview. Okay, so the right answer turns out for this question. So I would encourage you to take a guess before I reveal the answer. But the right answer turns out to be C. So that you only need P to be like roughly 1 over square root T. So like only like if you reveal me like roughly just square root T fraction of the input, then you can already get the square root T regret. Okay, so that's our result. So like our first main result is that for this binary classification problem in this preview model, and in general, like let's say VC dimension is D, the guarantee that you get is min of T. Okay, of course, like the regret is bounded by T. So the real terms are D over P plus square root dt. So what does this mean? It basically means that in the beginning, like as you increase P, so maybe this figure is more important. So the figure shows that as you increase the sample size, in the beginning, your regret is very large. It's like capital T-ish. But as you increase the sample size, it goes down like a 1 over x curve. But at some point, like once you reach something like a square root dt regret, where you reach this statistical threshold, like the square root t, you cannot go below square root t. After that, it basically remains roughly like up to constants, it basically remains at square root t. So again, like, so the answer has basically two terms. On one side, you have the d over p term. That comes basically to some kind of learning this adversarial sequence, getting past this binary search example. And the other one is the square root t kind of a term, which is this noise floor. So that's the main result. And then turns out you can also extend and get like a generalized result for multi-class settings. So by multi-class setting, I mean like the labels need not be just 0, 1. So you could have like thousands of labels or potentially even infinite number of labels. And you can again get some similar results. It's in terms of something called as the DS dimension and Nat dimension. I won't even define what these dimensions are, but basically you can get something similar looking guarantees. So usually Nat dimensions are better, so smaller than DS dimension, so you get some bounds like this. In particular, this bound is independent of the number of labels. So people ask this multi-class classification is more interesting when the number of labels is infinite. Then what kind of bounds can we get? And turns out, yeah, you can get something similar. And by the way, like theorem 1 has also a matching lower bound, like precisely up to constants. Theorem 2 has a matching lower bound, but up to polylogs. So polylogs are independent of the number of labels, but polylogs do depend on like PET and those kind of things. So theorem 2 is like tied up to polylogs. Theorem 1 is tied up to even constants. Good. So in the rest of the few minutes, I'll basically give like a high-level idea of how the proofs go. And like again, the intuition to keep in mind is that the first term is coming basically to get over this adversarial sequence. Okay, and good. So let's go over theorem 1. So the first approach, I'm going to discuss multiple approaches. So the first approach is maybe the simplest one, is basically something like we're given this sample preview of size PT. Let's just run some offline learning algorithm on it. like some empirical risk minimization, which is known to do pretty well. And let's just play that for the remaining input. Okay, so the remaining 1 minus pt input, I'm just going to run this algorithm that whatever I choose. Good. So now the question is, how well does this algorithm perform? This is like one of the simplest algorithm. So once this is the algorithm that does work when p is a constant. Okay, so you can show that the, let's say, like VC dimension is, let's say, 1, because let's say I don't want to worry too much about dependency on D. So the claim is that the regret will be something like square root T over square root P. And the reason is like the following. So you're given like PT samples up front. So recall like this epsilon squared versus uh, epsilon. Like, so if you're given like basically K samples, you get something like 1 over square root K. Like you can learn this threshold up to like a 1 over square root K factor. Hence, if you're giving PT sample, you'll basically be getting like learning this right threshold up to like a 1 over square root P theta times like T times 1 minus P in some sense, like the T-ish, like you still have to receive the remaining T. So the right answer turns out like this will give you something like a square root T over square root P. This is much larger than what we have above. So like above, like to give you an example, let's say if P is something like 1 over square root T, the above bound will only give you like square root T, like theorem 1 only gives you square root T regret, whereas this will give you something like T to the 3/4. So this is like, okay, it says that something can be done, but it's pretty weak. So it gets you to T to the 3/4 when P is like 1 over square root T. Good, so we want to do better. So let's now look at the second approach. So the second approach is basically like, so for people who might have seen like more of online like classification problems, at a high level, like now you have to go into something somewhat deeper. You have to like apply some like not a black box offline learning algorithm. So the high level idea is, okay, we want to come up with some kind of a cover for this hypothesis class. So you have this large hypothesis class, infinite sized hypothesis class, but I want to work with like some finitely number of small number, like finite number of hypotheses inside this class, which morally captures most of the hypotheses, like all the hypotheses. Like basically, as we know, cover in some other settings, like that every hypothesis is kind of close to some hypothesis in my finite cover. And I want to use that followed by some kind of a multiplicative algorithm on this finite class. And so precisely what you do is like, okay, you receive this preview. So on this preview, look at every possible labelings your hypothesis might be, like look at kind of the projection of the hypothesis class onto this preview. So basically look at your preview, which is of size PT, every possible labeling. The first thing gets like a plus, second thing gets a minus, third thing gets a minus, fourth thing gets a plus. So every possible such labeling pattern that I could get on my preview. Okay, so I'm going to imagine I'm going to basically cluster these hypotheses into pieces where each piece represents a labeling pattern that I observe on the preview. Good, so this is all done. Like I don't know which is the optimal hypothesis, but okay, I know the hypothesis class. So this is all information theoretic. So I know the hypothesis class. So I can kind of partition the entire hypothesis class based on whatever pattern I'm observing on the preview. And for each pattern, I'm just going to observe, like choose an arbitrary representative. Like from each of this cell cluster, just take one of the hypotheses. That kind of the point will be that this hypothesis represents this entire cluster. So now the remaining of the algorithm will basically be I'll just run multiplicative weights on this representatives. The claim is that this will give me the right guarantee. So at a high level, like why this works is the following. Firstly, let's look how many representatives we'll be getting. So, so recall we are having like some PT samples. This is the number of samples. So this is the crucial fact about VC dimension. So like, I mean, a classic fact, I mean, we need to use somewhere the fact that it's VC dimension. It's what is the property that it biases? It basically biases the following thing, that if you get some K number of samples, like K points, then the number of labeling patterns that you can get is just going to be something like K to the D. It's not going to be D to the K. So naively, like let's say if you have VC dimension 1 or 2, like naively things could be blowing up like you have K points. You could possibly be getting like any possible plus minus labelings. So you get like 2 to the K. But VC dimension makes sure that you get like only poly K kind of. So VC dimension is constant. So that's precisely what you exploit. So you get something like PT to the D. like there's this over D. So this is the number of hypotheses. So this basically shows that, okay, the number of hypotheses is not too much. So hence, if you run like multiplicative weights, that term is going to be something like square root dt. Like if you substitute like the standard square root t square root log n term, multiplicative weights, capital N is going to be some like exponential in d. So you get square root dt. This is one term. And plus I need to also accommodate like what is the error I'm getting from like the fact that I'm not working with all the hypotheses. Like you want to argue that from each cluster, whatever hypothesis I've chosen, they're like somewhat close. So that's the other term that you pay. So this comes out from like something called like realizable learning and all. I mean, if you know, like, but basically this can be also worked out. So that basically is kind of the entire proof that you can get bounds which are somewhat similar to above. The catch, however, is like it's going to lose you some extra polynomial factors. So you are correct. So you get the square root dt term, which is this term from the multiplicative weights, and you get this approximation error, which is the d over beta. So both of them are correct up to polylogs. So we are still off by logs and polylogs. So now the final approach, the third approach, which turns out to give the right answer based on chaining and all. So that requires more work, technically more interesting. It basically shaves off all these logs. So the idea basically at a high level is that, okay, currently we were looking at every possible labeling pattern of these hypotheses, like trying to project it on the sample preview. Instead of looking at, like, so you do look at, but like these representatives, these projections, they are not arbitrary. They have some kind of connections, like they're obtained from the same sample. So the idea of chaining is basically rather than just doing like the entire preview, subsample your preview. So like at different scales. So like you have something like the finer scale will contain all of the m points. Then you have like a subsample of size m over 2, m over 4, m over 8, each of them. So this you can use this subsamples to define some kind of a hierarchy of these hypotheses, and then apply some kind of a chaining argument. So this is like much more technical. Like you basically think of now any hypothesis as like going like starting from some root, like going along this path on this like via this subsampling, and there you like now apply some kind of a chaining. So this is much more technical. So I'll skip this right now. But this process allows you to shave off the logs. So basically, this guarantee that we obtain, like d over p plus square root dt, this is tied up to constraints. So that's theorem one. And I'll briefly quickly sketch over the multiclass theorem. So multiclass theorem, again, you want to get again similar bounds, but now the dimensions are like some ds dimension and Nitrogen dimension. So this work basically like, okay, I mean, I don't want to get into details, but the naive approach from last slides don't work because the number of labels could be infinite. It's not just like dog and cat. It's like every possible, like infinitely number of labels. So even if you look at the projection onto like your preview, that's already going to be infinite. So you cannot just learn like something like multiplicative weights even on that projection because it's going to be arbitrarily large and many things fail. Fortunately, what we can use is we can exploit like some very recent works on. So interesting, like multiclass classification was actually not even understood offline. Even the offline learning aspect was very open until this year. So only this year there have been like these works of Cohen et al. And followed by like a follow-up of Chirag Pabaraju. So they basically kind of resolve this question offline. Offline, what's the right dimension and what's the right dependency up to some polylogs. So we are able to exploit basically their machinery and more or less like black box recover our results from just the results of their guarantees combined by like natural intuitions from our approach. And I'll skip this thing, but like basically the point becomes that you can still somehow, even for multiclass setting, it is possible to come up with representatives, like finitely many representatives, and run some kind of a multiplicative weights on it. So to summarize, we started off with this classical setting where VC dimension, like this threshold example, where VC dimension is 1, but Littlestone dimension is infinite. And the question was really, can we do something better? And random sample, like if I give you like the sample preview, it does allow you to do much, much better. So you get like on the binary class, you get like the right sharp transition. In multi-class, we get it right up to like some polyglot factors. Yeah, so this allows you to go beyond worst case for these online classification problems. And this sample preview model is like very interesting. It has, as what I was saying, like it has been already studied for many other online algorithms. Like problems, such as like online set cover, online load balancing, online matching, and so on. But yeah, we show in this work that it's also very interesting to explore this model for this online classification problem. Some future directions are like, one is like, okay, can we make this algorithm efficient for some structured classes? So currently everything was information theoretic because the hypothesis class was infinite. But if you have some structure on the hypothesis class, classically it's known that at least the statistical learning, offline learning, you can do polytime algorithms as well for some nice classes. So can we obtain similar guarantees for this online setup in the preview model? And then the other main question is to extend this sample preview model to other problems, like not necessarily even online, and definitely online problems. You can study this preview model for any problem in any model, like a preview model, whenever you have some notion of time. So it could be like a streaming problem, it could be like a dynamic algorithms problem. Whenever you have some notion of time, you can study the sample preview model, and then you might want to minimize your regret, your competitive ratio, your space, your running time. Any of these things can be studied, which are interesting to explore in the future. And that's it. Thank you.